Okay, so today we're beginning antiderivatives slash integrals. So we have integral notation here, which is this big S, and I guess I should start by introducing the concept of an antiderivative and in a way the concept of an integral. So the two these two notions are related to one another, but we don't realize what their connection is until we touch upon the fundamental theorem of calculus, which happens later. So we sort of show you both of these concepts just to start off with, just to prime yourself on them before we show you how they're connected. But so an antiderivative is just the idea of trying to figure out the function whose derivative is the given function. So the antiderivative, let's say, of some function f(x) is going to be some, Peter's lagging a little bit, strange, is some capital F of x such that taking the derivative of the capital function gives you the lowercase function. So it's a convention that we use where we use the capital version of a function name to denote the antiderivative. But yeah, so this property is what defines being an antiderivative. And being an integral is pretty much the same thing. So an integral we can think of effectively as being the antiderivative, but that's technically using fundamental theorem of calculus. If you look at the definition of an integral, you learn about this as being a Riemann sum, a sum of the area below a curve, which we get introduced to that concept on like the third page, and then I guess the rest of the homework. But yeah, so maybe I'll say this and the integral. Which we can denote like that. Integral f of x dx is area below a curve, and normally it'll indicate for us from what values of x. So x from a to b, for example, is the area below the curve. And then the fact that these two notions are related to each other is fundamental theorem of calculus. I think parts 1 and 2 both are relationships. Yeah, so yeah, just FTC. Okay. All right. So now let's go ahead and look at some of these. So you have to think about like derivatives in reverse, basically. So for the first term here, this 2e to the x, well, you should think that, well, because the derivative of e to the x is just e to the x, the integral is going to behave similarly. So you're just integrating e to the x, you're going to get e to the x. For this 9x squared is a little bit more tricky. So if you want to think about power rule in reverse, right? Power rule says that you normally bring the power down and then subtract 1. Here, we're going to want to bring the power up and then divide. So the next term is actually going to be, why is my cursor being so slow? Second. Yeah, I don't know. Okay, so yeah, it'll be this, and you can kind of check this by then taking the derivative of this term and seeing that you get 9x squared. For the next one, I'm going to want to introduce the general formula for power rule for integrals. So power rule for integrals says if you're integrating x to the nth power dx, and so this is just for any number n, well, what you would do is you add 1 to the power, and then you would divide by n plus 1. And then you can tack on a plus c. So the reason for us to put the plus c for all of these formulas involving integrals is because technically you can vary your function up and down by a constant. That's what the plus c indicates, because you can take the derivative and the constant is going to disappear. So the answer for something like this, an indefinite integral, where we don't have like the endpoints of our integration, is going to be a function plus c. You have to have that plus c, otherwise you're technically wrong, because it's a whole family of functions that satisfy the statement of being the antiderivative. Okay. So for this third term, n is 3/5. So we add 1 to 3/5, that we get 8/5. And then we would want to divide by 8/5, but I may as well reciprocate this instead. So just to make it look a little bit more clean. And then the very last part is we put a plus c at the end. I'll get to there's one caveat to this power rule, which is that n cannot equal -1, since if it were, then this wouldn't be defined. In this case, you have a separate integral. I may as well introduce this now, but we'll see that we'll see it right here in 1c. So if you encounter a x to the negative first power, which is just a 1/x dx, this is a different thing. It's ln of x, but we technically put absolute values on it in order to enlarge the domain of the function. But what you can do is you can think through your derivative rules and recall that the derivative of the log function is 1/x. Right? So that's why we have this. Okay. All right. Yeah, back to the problems. Okay, so integral of cosine, you should think what function, when you take its derivative, gives you cosine, and that's going to be sine. What function, when you take its derivative, is going to give you secant squared? Well, you should think tangent. And then what about a function whose derivative is sine? Well, you should think negative cosine, right? There's going to be a sign flip that happens when you derive cosine. So you want to put down -5 cosine x, and then again, plus c at the end. Okay, what about the secant tangent? Well, thinking through your derivative rules, you should think of secant. And since this function is in terms of theta, we should use theta. Okay, and now we have this 3 times 1/x, 1/theta. So it'll be natural log, 3 natural log of absolute value of theta, and then plus a constant. And then for d, well, if you pull the 4 out, then you have a 1/1 plus x squared. So hopefully that also looks familiar to you. You just have to think through the derivative rules for the inverse trig functions, and you'll know that this is inverse tangent. So inverse tangent of x. Okay. And then for these last two, I actually want to think of them as power, as x to some power. And then I want to use the power rule for integrals here. So for the x to the 1/2, I add 1 to the x, and then I will divide. So x to the 3/2, and then we divide by 3/2, which is the same as multiplying by 2/3. And for the last term, we have x to the -2nd. So we add 1 to that, we get x to the -1st. We would then divide by 1, but that's just the same as multiplying by -1. So that's just going to flip the sign here from a plus to a minus, and then tack on the plus c at the end. So those are all of number 1. Any questions so far?
I have a question about the online homework.
Okay. So I don't have that in front of me, but you can,
Well, it just
if you want, you can share that with me.
it doesn't like when we type in the C. And I didn't know since during the lecture yesterday, we always added the C on the end and as well as this homework. So why doesn't the online one allow that?
Well, I would check what the what the online homework is, like what it says specifically. I don't have that in front of me. I can try to pull it up though. Which homework is it we're talking about?
19.
Which online homework is it? 19. Do I have 19 downloaded here? No. All right. Yeah. Give me a second to try to find it, I guess.
It looks like it already has the plus C at the end of it.
Okay, yeah, so that was what I was going to check. So I think it just doesn't require it because it already has it stated at the end of the prompt. Okay, so I'm not going to check it myself then. I'll trust whoever just spoke. All right. Okay, any other questions? No? Okay, well, let's keep going. So for number 2, it gives us it's basically asking us to do the same thing. It's just phrasing it a little differently. So here we've got this the derivative of f, and we want to find its antiderivative, which is just the original f. And it also gives us this condition here. So this would be called, I guess you could call it an initial condition. What it's going to do for us is it's going to specify the specific value of c that we need. Since this actually pins down a single point that our function has to pass through. All right, so, well, f of x, I guess the first thing I could maybe do is I could write that this is going to be the integral of f prime of x dx. You don't need to say that, but I'm just doing that to explain my thought process. So we're going to integrate the cosine of x plus 2. So when we do that, we would get a sine of x plus 2x plus a constant. Okay, now let's see what happens when we plug in this condition. So f evaluated at pi is going to be sine of pi, which is 0, plus 2 pi plus c. And all of that's supposed to equal 5. So that we can solve for what c has to be in this case. So c is going to be 5 minus 2 pi. Okay. And then, so we figured out what c needs to be in order to satisfy both of these two conditions. The last step would be to rewrite everything, where we then substitute in our c value, because this, in a way, I don't know what this calls it. Doesn't really. Yeah, so in a way, this technically isn't a function because that c is a parameter that varies. But once we fix our c, we definitely have a standard type of function. Okay, so now plus 5 minus 2 pi. So this guy is our answer for the problem. And then number 3 is asking us to do the same process, but twice. We have a second derivative, and we want to go back to the original function w. So we need to integrate this twice, and it tells us these two conditions, both of which are going to fix the two different constants that'll show up. Usually we integrate this step by step, but sometimes it might make sense to do both integrals first and then solve for the constants. Here, we're just going to do it step by step. So first, we integrate once. That's going to bring us to w prime. I'm not going to spell out the integral, but we just integrate this 5e to the x plus 2, which is going to give us 5e to the x plus 2x plus c. And then we can use the first condition, w prime of 0. When we plug in 0 into this function, we get 5 plus c, and that's supposed to equal 3. So we get that c is equal to -2. Okay. Yeah, so maybe I rewrite that. So now w prime is 5e to the x plus 2x minus 2. We integrate this function, which is going to give us w of x. And term by term, 5e to the x plus x squared minus 2x plus another constant. I'll say plus d, since I kind of want to separate these two different constants from each other. Okay, and now we use the other condition. So w of 0 is supposed to equal 9. When I plug 0 in, I'm going to get a 5. These two terms are both 0, and then I get plus d. So that's equal to 9, which tells me that d is equal to 4. And so we now have all of the constants figured out. We can just recopy the function for w, replacing in the constant of integration that we just found. So there we go. All right, we okay so far? Okay, great. All right, so 4 has a whole bunch of parts, but I start out in the same way. It's just that instead of having actual values for our constants of integration, we now have some stuff that looks a little different. So we have variables. So yeah, we have h naught and v naught, and we have these as our conditions. So yeah, just pretend those are numbers. And we start off with this statement about the second derivative, and we basically have to do the same thing. We have to integrate it twice, but it separates it for us. So, all right, first of all, the first derivative, h of prime of t, we just integrate that this is a constant function. It's a function whose value is always -9.8. So I don't know, maybe I'll spell it out in this case. So I'm integrating this dt with respect to t. And so I get -9.8 t plus a constant. And you could say plus c and then plug in this condition, but that's just going to give us that the constant is supposed to be that value. Like, so we kind of know like that it's going to be plus this v naught. If you want to, you could, I don't know, write out more things. I think it's clear that that's the constant. The next thing is to integrate this one more time, which will give us the function h of t, function for height. When we integrate that, let's see, this is going to be divided by 2. So 4.9 t squared plus v naught t. And then again, we would have plus a constant. But then looking at this condition for h of 0 equals h naught, that's going to tell us that the constant has to be h naught. So there we go. So that's part B. For C, it wants us to basically plug in this information that it tells us. So the height that we start off at is 2 meters. So this is actually our h naught, and then this initial velocity is going to be our v naught. So that's all it tells us, is it just specifies the two constants for us. So we can rewrite what we found, then plugging in those constants. 15, that doesn't look like a 15t plus 2. Okay. And then D and E are just working with this parabola. The only thing is that these values aren't picked out to be nice, so you end up with some very messy stuff. Well, I guess I'll ask, like, so how would you actually figure out D? What equation do we need to solve? So someone said that we solve C. Okay, well, that doesn't tell me everything, but I guess you're sort of saying it. So we need to solve that h naught is equal to 0. So if it hits the ground, that means that the height has become 0. So all you gotta do is h of t equals 0. And there's a process to do that. So since this quadratic isn't so nice, we have to use the quadratic formula for that. Okay. Since my pen is kind of laggy today, I'd rather not fill out all of the quadratic formula, but you should be able to do majority of that, I guess, by hand, just to show some of your work. So quadratic formula here. So that's for you to fill out on your own. And you'll eventually have to use a calculator to figure out some decimal approximation, I would say. You kind of need a decimal approximation. Otherwise, you get some, well, I didn't simplify it. It's like minus 15 plus or minus the square root of 264.2 all over negative 9.8. It's a terrible number. So yeah, about this much. For E, well, what time will the ball reach its maximum height? Yeah, so similar to the type of material that we cover, like in the last on the last homework. Maybe it was last homework. Maybe it was, or maybe it was like the homework before that. But to find the maximum height, we can like set the first derivative equal to 0 and solve, and that'll give us a critical point, which is going to correspond to a maximum in this case. So we can solve h prime of t equals 0. That's how we would go about E. And in this case, well, I guess I don't need to look at that. So the derivative set equal to 0, that's negative 9.8 t plus 15, we would set equal to 0, which would give us that t is equal to 15 divided by 9.8 seconds. And there isn't really a way to make this look any nicer. You could, maybe you could get rid of the decimal point, but you still get a nasty fraction. So I just left it as that. And then what is the maximum height itself? Well, we take this value and we plug that into the height function. So plugging in, we would get 15 over 9.8. Plugging in that. Yeah, again, I don't know. Doing it by hand would be terrible. So you end up with a decimal that's approximately this. So that's that. So, I mean, yeah, hopefully there aren't any questions on that. Try to do one more page. I think we'll end up stopping at that. Defined. So now we start looking at something that is a little different from what we've been doing. So in these first 2 pages, we've been working with the integral symbolically. This third page, we start thinking about the integral geometrically, which we can especially do because it has these limits of integration. So now we think of the integral as being area under a curve. And so in part A, this is area under the curve from -1 to 0. And so that's the area of this triangle, which we can figure out. That's 1/2 times 1 times 2. So that's just 1. For B, area under the curve. So because the function itself is actually below the x-axis, we treat the area as being negative. So the region that we would calculate is, I'm going to shade it and I'm going to erase it, but it's this part that's I just shaded. And we count this area negatively because it's below the x-axis. So technically, when we talk about the area below curve, we're talking actually about the signed area. So the integral measures the signed area. All right. So for this, I don't want that color. So for this, this is a triangle with a base of 6 and a height of -4. And so I get a -12 for part B. Now for part C, notice that the only difference is that we've switched the order of the integral. So instead of going from 0 to 6, we're going from 6 to 0. We always read it from like bottom to top. And the thing is that the order does matter. Okay, so we normally want to go from left to right. Since we're going from right to left in this case, what happens is this is going to flip the sign of the answer. So if I wanted to spell this out in detail, I would say that this integral is actually equal to negative of the integral from 0 to 6 of the same function. And this guy is part B, so we just end up with 12. We just negate the part B. And lastly, for this part D, we have integral from -1 to 6. So this is kind of giving us another property of integrals, which is that we can add the how do I want to say it? The intervals add in the way that you would expect. So we previously calculated the integral from -1 to 0. We also calculated the integral from 0 to 6. And now we're being asked to find the integral from -1 all the way to 6. So like you'd expect from your geometric intuition, you'd expect that you could just add the 2 previous results in order to calculate the overall thing. And you absolutely can do that. So one way you would state this would be, I'm going to abbreviate this. So instead of writing the full g of x dx, I'm just going to put this integral symbol and then plus this integral symbol. So just know, like, you're not going to see that in a textbook. This is kind of just a notational shorthand to say it's the integral g of x dx plus another integral g of x dx. So you see that the intervals add up. And so we can say this is 1 and then plus the -12. So this is just adding parts A and B together. And so you end up with -11. Maybe I'll box the answers just to make it a little bit more clear. The rest of it's kind of scratchable. Okay. So yeah, hopefully that's clear. And then I guess the last thing that we can talk about for today. Let me think, do I want to? Yeah, next time next time is a little bit more tricky. Okay, the last one's number 6. So we have this idea of the left endpoint approximation. So how do I want to explain this? So there's kind of like an animation that you can imagine, or you could probably look up what a Riemann sum is on Wikipedia or YouTube or anything like that. The idea is that we approximate the area. So in this picture, we would have this region plus this region plus this region if we're integrating from 0 to 6. Okay, I'm going to probably erase those points next. I'm just trying to illustrate. So we have those three regions that we would need to sum up. And the thing is that that's kind of difficult to work with because these are not simple shapes, right? In the previous, we had triangles, so we could easily calculate the area of a triangle. But here we've got these, I don't know, non-polygon type shapes. So the idea is instead we approximate the region using rectangles, and then we just use more and more rectangle. Well, the idea is if we use more and more rectangles, that is, those approximations will approach the actual area. So the idea is always to say we're given a function like I don't know, if we're given, I'm trying to make this look simple. Say we're given like this kind of region. The idea is we from A to B. The idea is we always subdivide this interval from A to B into however many regions, and we draw rectangles for each of these regions. And that the more rectangles we draw, the closer the approximation will be to the actual area. And we might overshoot or undershoot depending on how we specify the rectangle. So that's where this statement about the left endpoint approximation comes into play. There are a few different, the idea is that there are a few different ways we can pick the height of the rectangle to be, which is, I guess I'll now try to do on top of this drawing. So, and also, okay, it specifies for us, we have n equals 3 subintervals. So that means that we take the length and we subdivide it into 3 equal pieces. So since this is a length of 6, 0 to 6 is a length of 6, we want to divide it into 3 pieces. So each piece is going to be length 2. And so we have these parts. Cursor's being a bit bothersome. Okay, and so we need to specify a rectangle from 0 to 2, a rectangle from 2 to 4, and a rectangle from 4 to 6. And its height is going to represent what we consider the area of the function to be for that subinterval. Left endpoint means that we want to match on the left endpoint of the interval. So, for example, for the subinterval from 2 to 4, the height that we assign this rectangle is going to be the value at 2, the value of the function at 2, which is namely here. So we would specify and get this rectangle for this subinterval. So left endpoint would do that. If instead we were using the right endpoint, we would have to make the height of this subinterval match the value at 4 instead. And there's also the notion of a midpoint approximation, although we typically don't talk about that in this course for some reason. But the midpoint would just use the value that lies in between the ends of the subinterval. So then you'd match it along the height at the midpoint, which is 3 in this case. So there's all these different approaches, but they're all just to specify what the height of the rectangle should be. And then later on, we'll see, like the idea is to then take the limit as we let this n, this number of subintervals, let that go to infinity, and your rectangles are going to get thinner and thinner. But then the sum of all their areas is going to approach the integral, the actual area below the curve. And let's go ahead and do it for the rest. So for the subinterval from 0 to 2, the height has to match there. So it's going to be a height of 2. And for the subinterval from 4 to 6, the height has to match the value at 4. And so we end up with this rectangle of height -4. And so you can see like this is a very coarse approximation, and it really does not match the curve very closely at all. But that's because n is equal to 3, not 3 million. Okay. Right. But for this approximation, what is the actual area that this calculates for us? So the first thing is we're calculating the area of a bunch of rectangles. Since all of these rectangles have the same width, I'm just going to factor that width out first, right? So 2, and then I'm just going to write down all the total heights. So we got a height of 2, we have a height of -1, and we have a height of -4. So this is just, in general, I would write it like that, but you could just not use those extra parentheses. So this is 2 times -5 -3. So we get -6 as our approximation. Okay. Yeah. So I guess that's all I want to talk about for today. Are there any questions? No? No questions? Okay. Well, the next time we'll continue with the rest. I would rather not do one more page. So yeah.